So in the first part of this video lecture, we have seen two exact formulas to compute probability expectations of discrete random variables. One is the classical formula, just add the products of all possible values this random variable can take by the probability that the random variable takes that value. From there, we got a very convenient formula for the expectation of x in terms of summing probabilities that x takes values larger than n, summing that over n, and that will be very convenient because now in this last part of this video lecture we're going to prove this integrability condition. And what the condition says is a random variable x, or even an extended random variable x if we want, it is integrable if and only if these probabilities here are summable. And it's very interesting to, when we're talking about probabilities which are summable, we'll see towards the end of this module many interesting things that we can say when probabilities of certain events are summable. Before we start the proof of this proposition, let me go back here and mention that it is important, or it's worth remarking, that in the proof of the first proposition, and I'll let you figure out the details, as well as in the proof of the second proposition that we have given, we never used the fact that we are in a probability space in the sense that the measure of the sample space is finite and equals 1. These identities, they work for every measure space. In contrast, this proposition really is only for probability spaces. So let's see now its proof. Now to prove this, we start by defining a random variable. Take the random variable z to be simply the absolute value of x. And now what we want, so we can substitute this here by z, and x being integrable is the same as the expectation of z being finite, because we already know, well, z being non-negative, its expectation is well defined and it's non-negative. And now take also y to be this floor notation. So this notation means rounding z down to the nearest integer from below. Okay? So it is the largest integer which is less than or equal to z. And in case z equals infinite, we can say this is also infinite. Okay, so defining y this way, we now can explore this condition here. And how is that? Well, y only take non-negative integer values, possibly plus infinity, so we can use the previous proposition, this one here, to write the expectation of y to be exactly the sum over n natural numbers, but actually we don't care if 0 is part of the sum or not, for the purpose of this proposition. So for the probability that y is larger than or equal to n. And now we just have to notice the following. If a number is larger than or equal to n, then rounding down that number to the nearest integer from below, it's still larger than or equal to n. And vice versa. If it's smaller than n, writing it down, it will be even smaller. So this is equivalent. A number is larger than n if and only if, rounding it down, is still larger than n, because n here is a natural number. And well, this is exactly the event we have upstairs, the event under consideration. And now all we need in order to conclude is the following. Y is always less than or equal to z, but z is always less than or equal to y plus 1. and these are all non-negative random variables, we can use property of the expectation being Lebesgue integral, it is monotone, so we can take expectation. So say the expectation of y is less than or equal to the expectation of z, which is less than or equal to the expectation of y plus 1. But wait, 1 is an integrable random variable, so whether we add it before or after taking the expectation will not matter. So we can rewrite this as the expectation of y plus the expectation of 1. The expectation of 1 is 1, because we're talking about a probability measure here. And, well, what we have is a number which is squeezed between another number and that number plus 1. And, well, if one of them is infinite, the others will be infinite as well. If one of them is finite, the others will be finite. And which means the expectation of z is finite if and only if the expectation of y is finite. But we already know what the expectation of y is. It is the sum here, which is exactly this sum here. So this concludes the proof of this proposition, and this concludes this video lecture.